Okay, so let's kind of finish up that vector assignment to make sure everybody's cool with what you need to have happen. So let me kind of give you kind of some estimates of what should happen, okay? So and this is just kind of, even if you just make a sketch, okay? So like on number 11, you have a plus b plus c. You are actually going to go through and you're going to find all the x components and all the y components and add them up. But even if you make a sketch, you can get an idea of what should happen. So if you look on like number 11, you've got vector A, vector B, vector C, boom, there's a result. So even if you just make a crude sketch and you draw these just tip to tail, you got to figure that that angle is going to be somewhere between 0 and 90 degrees, okay? Probably closer to 90. And this is just making just a crude sketch, okay? That's all. So what you're fundamentally doing, and again, this is the whole idea, by deconstructing these vectors, what you're doing is that you're saying, okay, I'm going to take A's x component going in this direction, and C's x component coming back in this direction, and the net effect of those two tells me how far I'm going in the x direction, okay? So that's the net effect, okay, of that going out this way, this one coming back, this is how far I end up in the x direction. Then I've got this y component of b, which is all in the y, and then I've got C's y component, which is going up like this. So to go up, I'm basically going to go up vector b, and then whatever the x component is of C. So now what happens is that now I've got a right triangle in here. Now I can do the Pythagorean theorem. Now I can do inverse tangent. That's how I'm going to find resultant. That's how I'm going to find that angle. So if all goes well on that a plus b plus c, you should have a resultant somewhere around 7 and an angle somewhere in the mid-60s. Okay? That's where you should end up. On number 12, you should end up something around 4 as your resultant, and the angle should be around 170. Okay? It's an ish, but it shouldn't end up there. And then on 13, again. So on number 13, there's two ways you can approach number 13. One is if you just make what's called a free body diagram sketch. So you got 5 newtons at 60 degrees. Okay, so here's this 5 Newton force. And then you got 10 newtons at 80 degrees. Okay? So it's like this. Evan's kicking the soccer ball this way with 10 newtons. I'm kicking the ball this way at 5 newtons. Okay? So you got to figure the ball is going to go somewhere in between. So this, I cannot emphasize this enough. This is not the tip-to-tail method. This is just a free body diagram showing where all the forces are going to act. So like tomorrow when you all start your first lab on forces, this is one of the things you got to get used to the lingo. I'm going to say, hey, draw a free body diagram. You treat this thing as this is it. This is the object, whatever it is. A soccer ball, a block of wood, a squirrel, a penguin, whatever it is. Here's the center of mass. I got a force going this way. I got a force going this way. So, but the advantage of this is that it tells me, oh, this is where this thing is going to end up. Okay, somewhere between 60 and 80 degrees. Probably a little bit closer to 80 because the 10 Newton force was a little bit bigger. Evan's force when he kicked the soccer ball was bigger than my force. So it's probably going to go closer to here. That's as a sketch, okay? Free body diagram. Now, the other thing that you can do is you can sketch it tip to tail. And go, okay, here's this 5 Newton force, okay? Oh, that got ugly. No idea how that turned into a 5. There's my 5 Newton force. And then from the end of that, I'm going to draw at 80 degrees that 10 Newton force. Okay? And then boom, there's going to be my result. So, especially with forces, when you draw them tip to tail, and you're going to hear us talk a lot about this concept. Well, when you draw forces tip to tail, there's only one of two things that can happen. You have a resultant like this, which means you're going to accelerate, or you end up back in the origin and you're not going to accelerate and you're going to have a constant velocity. Every force problem that I'm going to give you can only play out one of two ways. I'm either going to make you accelerate or it's going to be the constant velocity. So as soon as if you see the words constant velocity, when you add up all of the forces and you draw them, you end up back at the origin. Now, that doesn't mean that you're at rest. It just means you have a constant velocity and you're not accelerating. So right now, all the forces acting on Adeline add up equal to 0. Gravity is pulling her down with a certain amount of force, but the chair is providing a force that's balancing that out. There are forces acting on her, but she's not accelerating. Okay? Now, I like Adeline. I've known since she was a freshman. Okay? I'm not going to do this, but I could walk up behind her and grab a hold of that chair and pull it out from underneath her. Now, when I do that, what's going to happen? She's going to accelerate. Because at that point, the forces don't add up equal to 0. It's an imbalanced force, and she's going to begin to accelerate. Okay? So literally, when I write a force problem on your homework, here's the first decision I have to make. Do I want Josh to accelerate, or do I want Josh to move at a constant velocity? That's it. You can't, oh, I'm kind of accelerating. No. Okay? You can't kind of accelerate. You're either accelerating or you're not. Either the forces add up equal to 0 or they don't. So in this situation, I know this thing is going to accelerate in this direction because that's the direction of the imbalanced force. Okay? So on that one, on number 13, you should get a force, and this is an ish, a little bit younger than where you are right now, and an angle, unfortunately, well, it's still a long way from how old I am, okay? Hopefully I'm not teaching it when I'm 73. If I am, because that'd be like 20 years from now, you all would be like 38. So if you all come back for your 20-year reunion, and I'm still in this room, you ought to go, Bergkamp, you've done your time. You know, go home. Go home. You've taught Newton's laws long enough. Go on. You fought a good fight. Now, on number 14, if you do the same thing just to make a sketch, so you got a 5 Newton force at 100 degrees, and then you got a 10 Newton force at
200.
Yeah, at 200, which is going to put you down here like this. So, boom, there's that resultant. So, again, just based upon a cursory sketch, that angle has to be somewhere around 180 degrees for that resultant angle. Okay, just making a sketch. So this is where your calculator will lie to you, okay, on this one, where you're going to find that angle, because what you'll see is that your x component is negative. The sum of your x components on 14 is a negative number. Should be like around negative 10, okay? And then your y component is going to be a positive value. So when your calculator lies to you, when you make that sketch and you have that negative number for your x component and a positive number for the y component, remember, this angle has to be given from that positive x-axis. So if you punch in your inverse tangent of that positive y over that negative x, your calculator more than likely is going to give you a negative value for that angle. Okay? We can't have negative angles. So this is why you have to make this sketch. So if your calculator gives you this as a negative value, just add that to 180 to get to here. If your calculator gives it as a positive angle, because this is what I would do personally, and again, this is just how I learned how to do it. If it were me, I wouldn't even touch this negative sign. Okay, I would just find this angle, and then I'd subtract it from 180. Okay, I wouldn't even punch in that negative sign, because when I learned how to do it, you know, you had this data, you know, this trig table in the back, and so you would physically take and divide this number and then look through this table and find out the angle that corresponded with that numeric value. So that's how, because calculators didn't do trig functions. So you would find this number, okay? And then look at that. And somebody posted on I don't know, Facebook, Twitter, was like, do you guys remember when Netflix showed up like it was a DVD? Yeah, and so it's going, my God, I remember when Netflix showed up in the mail and you're like, really? Perish the thought. Anyway, so that's what you guys can hold on to. It's like, I remember when Netflix came in the mail. I was like, wow, you're old. So it's a relative, thing. Okay. Anyway, so your resultant on number 14 should be around 10, and that angle should be around 170. Okay? We're good? Fantastic. Anything else you want me to go over? Going once, going twice. So make sure I get these assignments. I'm growing tired of late work. Okay? Get me the assignments on time. Okay, so let me hand out these lecture notes. For those of you that are in the studio audience, you will get these tomorrow.
Did you just put those up?
What?
You just put those up?
Is that Glenn?
Yeah.
Yeah. Yeah.
Are you using it today?
Huh?
Are you using it today?
Oh, what?
Are you using it today?
Huh? Yeah. Been a key component of what we're talking about.
Rachel left.
Huh?
Rachel left.
Did she?
She just left after you said
Rude.
I know.
I don't have the notes, I'm out.
Yeah, she said bye.
Oh, well, that makes all the difference.
No, she actually didn't actually say that, but she did leave. So.
Oh, what time I see party girl tomorrow? Okay. No, she's not. Jane's party girl.
I was gonna say.
Yeah,
I was like,
Janine's
wait.
pretty.
What's this party about?
Rachel's her sidekick. Okay.
Rachel takes the blunt.
Yeah.
Where Janine does.
There you go. Okay. So this has kind of become one of my favorite lectures to give, and it deals with forces. So this is what's known as a good news, bad news day for you all. So the bad news is that I have to talk between now and, when we get out of school. The good news is you don't have any homework, okay? So that's kind of the trade-off. It's rare that this happens. It happens today. It'll happen again when we do like gravity equations, and that's about it. So relish in the days that you don't have any homework. But it's just kind of cool, and I'm going to try and make it as entertaining as possible. So when you look at the whole history of science, okay? And yeah, there are books written on the history of science. You can actually get like a master's or doctorate in the history of science, okay? And it does have, it's full of like unique characters and stories and intrigue and egos and witch hunts and whole sorts of things, because they thought it was like tied in with sorcery. You look at Galileo and his conflict with the church over, motions of the sun versus the around the earth versus the earth going around the sun. And everybody kind of screws that up and says, oh, they disagreed with Galileo. Galileo was actually viewed as a brilliant mind. The problem with Galileo is that his ego got the better of him, and in writing the story about the motions of the earth and the sun, he lived in Italy and he made fun of the Pope in writing the story.
Oh.
That's what got him into trouble. It wasn't so much the theory, it was how he did it. Okay? It was like, Italy at the time, not a good time to make fun of the Pope. I'm just saying. So they just didn't tolerate that very well. So, like I said, there's this whole long story. So, even if you go back to like the ancient Greeks and Aristotle. So Aristotle, if you look at the history of science, is one of the first big hitters. And so one of the things that Aristotle said, and we'll talk about the views of Aristotle, was that his thing was that if you have a lighter object and a heavier object, so if I have like, say for example, this 20-gram mass and bowling ball, okay? So if we have a 20-gram mass and we drop that, and we have Hank the bowling ball and we drop that, Aristotle says, oh, well, there's more force acting on Hank, therefore Hank should fall faster than the mass should. And for like 2,000 years, basically from like 400 BC up until about 1600 AD, everybody just accepted that for like 2,000 years. And y'all would think, nobody bothered to test it? I mean, seriously. It's like for 2,000 years, no one bothered to take and test this. Well, there's a couple of things. Number one, they had a lot of things going against them at the time. Okay, England was being invaded by the Romans and the Germans and the Vikings. There was all this conflict, and they had the Black Plague, and
They were busy.
Yeah, they were busy. Okay, they were busy. Okay, they didn't have the internet, they didn't have lighting, they didn't have Oreos. For God's sakes, come on, they had other things to do. So in the Renaissance, okay, the Enlightenment period, as the story has it, Galileo goes to the Leaning Tower of Pisa, and he takes a small cannonball and a large cannonball. And it was kind of like a festival, okay? And this would have been like all the learned people of the region. It was like a state fair. And they would have all read and studied Aristotle's law of falling bodies. And everyone just accepted that because Aristotle said it was true. So Galileo has the audacity to go to the Leaning Tower of Pisa, as the story has it, and even if it's not true, it's a good story. And he takes a small cannonball and takes a large cannonball and drops them, and lo and behold, they hit at the same time. So that got Galileo into trouble too, oddly enough, because he was mocking Aristotle in the sense that he didn't disprove him. That wasn't the problem, but he did it in a very public manner. And it was just like, it was almost sacrilegious because, oh my God, Aristotle was held in such high esteem. And then you publicly disproved him. And I was like, oh, yeah, okay, whoa, talk about Twitter blowing up, okay, hashtag dropped objects, hashtag Leaning Tower, okay? So that kind of, but here's what happened though. In Aristotle's view of science, he didn't trust the senses. Okay, and this is going to be an important part of how Aristotle viewed the world. He says, look, if you think about it, everything that you have ever experienced, seen, heard, touched, felt, whatever, has all come through your senses. For you to sit there and hear me say the word Aristotle, it's very complex. So number one, I've got to form the idea that, okay, I want to talk to the kids about Aristotle. And then that signal has to go to my vocal cords and my lungs, and okay, I'm going to exhale, and I'm going to make my mouth and my vocal cords pronounce something that I think is the word Aristotle, okay? And then that's going to go out to all of you as a series of compressions, okay, as a sound wave that goes out. That's going to hit your eardrums. Your eardrums are going to vibrate. Those vibrations are going to send a signal through the inner bones of your ear to your auditory nerve. Your auditory nerve is going to send that to your brain. Your brain's going to process that quickly and go, oh, Urkam's talking about Aristotle. Oh, this is kind of cool, right? So it's actually very, very complex. When we study optics, you all right now are actually seeing me upside down because of how your cornea is built. The image in the back of your eye is upside down. But your brain has the capacity to flip it right side up. We're able to sense temperature, which is kind of cool, no pun intended. So you can put your hand on something, oh, how does it feel? Does it feel warm? Does it feel hot? You can smell things. Okay, whoa, how does that work? You can taste things. Ooh, how does that work? So everything that you've ever experienced has been filtered through your senses. And Aristotle didn't trust the senses. He thought that how you knew the world around you was by a well-thought argument. Right? That was his whole thing. Because he was a philosopher. He wasn't an experimental scientist. If you could ever go back in time, go back and be a Greek philosopher. It's a sweet gig, okay? You get to sit around, you're on the upper echelons of society, you get to wear a toga, eat grapes. You don't have to do anything, okay? Your justification is arguing things. That's all you have to do all day. It's a sweet, sweet gig, okay? So, So the pendulum with Aristotle was over here. You didn't do experiments because you didn't trust it. All you had to do was rationalize the idea. So as soon as Galileo dropped those two objects and they hit at the same time, that sent a huge repercussion through the scientific world. Now the pendulum swung to the other side. Now, no one in the scientific community was going to accept anything unless you had the scientific method to back it up. You could do the experiments, you had the math. I could do an experiment and then, Lauren could replicate it. She could read my results, she could read my lab, and she could get the same results that I could. If that didn't happen, then my experiment wasn't valid. If she couldn't replicate my results by reading what I did, there was no point doing my experiment at all, okay? Because mine wasn't valid. So no matter how justified it could be, if the results couldn't be replicated, if she couldn't do what I did, it was just garbage, okay? So, they figured out the gravity thing, okay? Now, for a while they thought gravity was magic. Have I told you all the magic story? Why they thought it was magic? Okay. I have to keep track of what stories I've told which class. And it makes sense, because, if I put my hand here and that that can of Dr. Pepper starts to move towards my hand, ooh, magic, okay? But if I do this and it falls towards my hand, oh, it's just gravity, okay? Not a big deal. Now, if I let go and it goes sideways, oh, that's magic. But if it goes this way, oh, it's just gravity. So, Newton was the first one to come up with a mathematical formula for the idea of gravity. And do not write this down, okay? I'm just pointing this out. We're going to spend a lot of time talking about this equation. But what he said was F equals big G, m1, m2 over distance squared, okay? So let's talk about the importance of this equation. This big G is just a constant, okay? And later on you'll see where this number comes from. But it's 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. That's called the universal gravitational constant. These are your masses here, okay? And this is how far apart the objects are. So here's all you need to know out of this equation right now. This number was actually found by a guy by the name of Henry Cavendish. Newton actually just said, hey, there's some constant of proportionality. I don't know what it is. I'm going to let somebody else figure it out. So all Newton figured out is that these are just the two masses. So here's the significance of this. To have a gravitational force, you only have to have two things. You have to have two objects that have mass, and to calculate that, you just have to know how far apart they are. So obviously, you all are gravitationally attracted to this big rock that we're on. Okay? It's a cool thing. If not, we wouldn't be here. You're also gravitationally attracted to the moon, to Jupiter, the sun. You are gravitationally attracted to the most distant electron on the most distant side of the universe. It's a gravitational attraction. So the only way that you could be in zero gravity, this is like the ultimate freshman idea. The only way that you could be in zero gravity is if you were the only thing that existed in the universe. Okay, that's it. Because if there is any mass anywhere else in the universe, you are going to be gravitationally attracted to that. So what that means is that no matter how big D gets, it's never going to go to zero. Functionally it will, okay? It isn't like, we had a full moon Friday night. It wasn't like you all had to worry about, oh, it's a full moon, I better hold on or I'm going to get lifted off the earth by the gravitational pull of the moon, okay? Now, when the moon was directly overhead, you did weigh a little bit less. It was like a tug of war, okay? You were being pulled towards the moon. Not enough to worry about, but you were actually gravitationally attracted to the moon. So, the other side of it is as the mass gets bigger, the gravitational force gets bigger. So this kind of becomes like a self-fulfilling prophecy. And if it wasn't for this idea, we wouldn't be here having this discussion. So if you look at what happened after the Big Bang, okay, hey, matter formed, it cooled, boom, we started having electrons and neutrons and protons. And then gravity started to kick in. And you had disturbances in this distribution of matter. And they started to clump together. Well, what happens is that the bigger the clump gets, the bigger the gravitational force becomes. So it becomes like this snowball rolling downhill. So once you started to form a star or a clump, then it would get more mass, and then it would pull in more material, and then as it pulled in more material, it would get more massive, and then it would get a stronger gravitational field. And so what happened is that eventually you got that hydrogen in a high enough density area and under a high enough pressure, under a high enough temperature, that you saw the first generations of stars start to blink on. Okay? And now, the only thing that comes out of the first generations of stars is hydrogen turning into helium. Okay? That's it. It's the only thing we existed in the universe. But then eventually, any star has a tug of war within its structure. It has gravity trying to pull it in because of this equation. But you also have an expansion force because of the fact that you have all this hot gas and this fusion and these extremely high temperatures. So it's a balancing act between the gravitational force trying to keep a star together and the expansive force trying to make it go apart. So eventually what's going to happen to our sun and any sun is that we're going to lose this battle because what's happening is that hydrogen is being turned into helium. Every second that goes on, like millions of tons is happening. And those sit there going, oh, man, that's just depressing. We are so screwed. Okay. The sun has been around for about 5 billion years. Okay? We got about another 5 billion to go, give or take about 10 seconds. We're good. Okay? Don't sweat it. We're going to screw this thing up well before the sun expands and engulfs us, so don't worry about it. Okay? Don't lose sleep over it. Yeah, just you're good. But because of the fact that we're turning hydrogen into helium and that mass is turning into energy, the gravitational field within the sun is becoming weaker. And so what's happening is that the expansive force is getting stronger than the gravitational force trying to hold it in. And that's going to allow our sun to get bigger and bigger and bigger and bigger and bigger and bigger and bigger. Okay? Like I said, don't worry about it. You're good. You can watch your TikTok videos and not feel bad. It's okay. Right? Okay. But here's the other thing that's important. This is what's known as an inverse square law. You're dividing by distance squared. So what that means is like if you double the distance, the force decreases by a factor of 4. If you triple the distance, the force goes down by a factor of 9. Okay? Now, or if you halve the distance, the force goes up by a factor of 4. So this is what's known as an inverse square law. It's directly proportional to distance squared. So the gravitational force can never go to 0. It's important. Without it, we wouldn't have stars. If you didn't have stars, we wouldn't be here. Because if the first generation of stars didn't collapse, you wouldn't produce carbon, nitrogen, oxygen, all the heavier elements that make us up. Okay? You wouldn't have iron for hemoglobin. You wouldn't have carbon, nitrogen, oxygen in your DNA. Bad things would happen. We just would not, physically, we would not be here. So if it wasn't for gravity being the great sculptor of the universe, we wouldn't be here. So that was the fundamental forces, and there's 4 of them. Okay, so if you look at your lecture notes, I talk about 4 fundamental forces. There's 2 of them that directly impact your life. One of them is gravity. Okay, that's the most common one. Okay, the gravitational force. It keeps you on the Earth. It keeps the Earth moving around the sun. It keeps our Milky Way galaxy together. Okay, it's kind of a cool thing. We want gravity to exist. You do not want to be an astronaut and be told, hey, we lost gravity. And you're orbiting the Earth and they call you and go, we lost gravity. Because you're screwed at that point because you're going to go off in a straight line away from the Earth and bad things are going to happen. Okay, so that's the first one, gravity. Now, the next one they knew about, but they really didn't understand. And this is what's called the electrostatic force. Now, the electrostatic force, and we'll spend a lot of time in the spring talking about this. Okay, for now, I'm just going to give you the equation. But it's F equals K, Q1, Q2, over distance squared. So if you look at these two equations, yeah, if you follow me on Twitter, I did a deal with Coulomb and Isaac Newton, so, and Mr. Bean. So if you've seen it, it's funny. If not, I'll show it to you. But here's the basic idea, is that you have a constant of proportionality times two masses divided by distance squared. This is a constant of proportionality, 9 times 10 to the negative 9. These are two charged particles, and it's divided by distance squared. So this is charge, measured in coulombs, which we will spend a lot of time talking about. This is mass, fundamental unit of nature, which is in kilograms. They're both divided by distance squared. They both have some constant of proportionality, and they're both going to measure force. Now, but here's the caveat. This will always work as long as you have two particles that have mass, okay? This only works if the particles are charged, okay? So this is a certain amount of charge, this is a certain amount of charge. So like neutrons, which are neutral, if you all remember from your Chem 1 days, okay? Neutrons have no charge. So neutrons never experience the electromagnetic force because of the fact that they don't have a charge. Electrons and protons do. So, I want to do some examples. So, give that camera just a little bit of a twist over here. Is anybody still zoomed in?
No.
Okay, then don't worry about it. You're
No,
done.
that's,
You're good.
okay, good.
We just have to worry about it.
I need a room key to some scanner.
Okay. And so if I put my hand right here, okay, my hand has a certain amount of mass, okay? Not a lot, it has a certain amount of mass. And this balloon has a certain amount of mass, right? So, as I bring my hand closer, I'm closing that gap, okay? And that gravitational force is getting stronger and stronger and stronger. Now, it really doesn't have much of an impact on the balloon. Okay, certainly I'm not going to be able to do some Jedi mind trick where I go, oh, I want that piece of paper, and I'll put my hand, and then eventually the paper goes flying off the table and up to my hand, which would be cool, don't get me wrong, okay? Especially as you get older, if you could just take your foot and like put it over something and then it would like stick to your foot, that would be cool. So, right now, this balloon is made up of, you have the material that makes up the balloon. We're going to do a lot of things with balloons, especially in the second half. But it's kind of cool if you look at what's happening on an atomic level inside that balloon. So what's making the balloon have shape? What's happening inside? Mr. Bird. If you say the word air molecule, so help me God, I will flip out.
No, I was going to say that it's
Okay,
got...
I hate the word air molecules. There is no such thing as an air molecule.
It's the air inside is exerting a force that's expanding its container out.
Pressure.
On an atomic level.
You're right.
And
Okay.
it's pushing like the...
But what's happening to make that have that pressure?
the particles are...
They're bouncing off each
What are these
other.
particles?
The air molecule.
The air.
atoms.
He's about to kill you.
Atoms, what are the two gases that make up
Nitrogen.
nitrogen and oxygen? Those are the two big ones, right? Okay, nitrogen is about 77%, and oxygen is whatever. Okay, those are the two big ones, mostly nitrogen and oxygen. So what's happening inside of there is that you can imagine, and we'll talk about, especially when we get into gases, imagine that you have like, gases are like a second grade classroom and they're full of these little hyperactive kids named Timmy, okay? And what's happening inside the classroom is that Timmys are like out of control and they're running around, they're bouncing off the walls, okay? And the teacher is like feeling that pressure and so are the walls because little particles are bouncing around. So if Timmy sits down, okay, and calms down, there's no pressure on the walls. So if I could take all of the nitrogen and oxygen molecules, not air molecules, okay? If I take all of the nitrogen and oxygen molecules inside that balloon and go, okay, everybody just chill out, the balloon would instantly deflate because there would be no particles bouncing around causing it to have pressure.
So that's like when you decrease the temperature of a balloon.
Exactly. So decreasing the temperature of a balloon is like taking the Skittles away from the Timmies, okay? So the Timmies don't have any energy. Now, if you heat up a balloon, That's like giving every kid in there like a bag full of Skittles. And they all have more energy and that increases the pressure, okay? Like I said, I can teach you all of thermodynamics with kids, second graders named Timothy. You get that. So right now, inside of here, you have billions upon billions upon billions of billions and billions. These tiny little particles of nitrogen and oxygen molecules hitting the sides of the balloon, and when they hit, they exert a pressure. They bounce off. And when they do that, that's what gives the balloon shape. Now, the latex actually appears solid. If you let this sit for a period of time, the balloon deflates, because over a period of time,
Air molecules diffuse.
yeah, so they're going to go through that latex, especially if you have like hydrogen gas. Hydrogen gas, if you fill it up, if you fill a balloon with hydrogen gas, because those are pretty small, this will actually deflate pretty quickly, because that hydrogen is so much smaller than the pores of this balloon, and they will escape out. So it's like, imagine that you have the room full of Timmies, but there's like little tiny windows, and some of the Timmies could, if they hit just right, can get out. Okay. So you have Timmies bouncing around, they're hitting this, they're creating pressure. It has a certain amount of mass. It's being pulled down by the gravitational field, right? This is why we have to have the string. So gravity's pulling this thing down, okay? Later on we'll talk about the buoyant force. There's a buoyant force that's lifting it up. We'll get into that later. So when I put my hand right here, every proton, electron, and neutron that makes up my hand is gravitationally attracted to every proton, electron, and neutron that's inside that balloon, okay? So we could go through and we could do this calculation. If I knew the mass of every particle that made up my hand, every proton, electron, and neutron that made up my hand, and every proton, electron, and neutron that makes up that balloon, I could find that sum total of all of these. And it wouldn't be very much. Okay? It'd be a really, really, really small number. However, if I take that same balloon, okay, I'm just going to rub it with this blanket, okay? Okay? So now, all right, put my hand there. Now I can do kind of this Jedi mind trick thing, okay? Whereas before, when I put the hand there, nothing happened. But now, because it's become charged, I can make that balloon move. So at this point, everybody's going, sorcery! Okay, where do you have the stake? Right? There was a time I would probably be burned at the stake for this. Number one, because I had a balloon which hadn't been invented yet, so I was a time traveler. Let alone the fact that I could make it move without actually touching it. So, if you look at this as being like magic, okay, this is magic because of the fact that I have it in my sleeve, I give it a rub, right? I put my hand there, whoo, okay? I can make it move without even touching it. So basically what's happening, on an atomic level, you have electrons. So if you all are familiar with breeds of dogs, okay? So the electrons are like the chihuahuas of the atomic world, okay? They're these tiny little yippy bits of matter. They go yip, 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 okay? And they go running around the nucleus. And they give it volume, okay? So we have volume because of the chihuahuas, otherwise known as the electrons. Now, inside there, you have the St. Bernards, which are the big kind of dogs, okay? They're really chilled out, they're massive, okay? They just sit there at the middle. So you have St. Bernards, the proton St. Bernards and the neutron St. Bernards. They're in the nucleus. And then around here, you have all of these chihuahuas going yip, 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 okay? And they're circling around, they're really annoying, but we kind of have to have them. Because if all we had was the protons and neutrons St. Bernards, we wouldn't be here having this discussion. If the universe only formed the chihuahuas, we wouldn't be here having this discussion. So it took a balance between the two. Now, that's a whole other discussion about why we have more matter than antimatter. We'll get into that later. So what happens is this. So here's the balloon, okay? And later on you'll see that the balloon has a negative charge. And so the balloon itself is charged. So what happens is that when I bring my hand close to it, the chihuahuas, okay, so this is negatively charged. So this has a whole bunch of like negative charge here. So what happens is that the chihuahuas that make up the palm of my hand don't like those chihuahuas, and they go, yip, 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 and they go run away. Okay, not very far, but they shift. And so what happens is that then within my hand, okay, you have the big St. Bernards that are stuck there. They're going, so, where are y'all going? We're just kind of showing out here, Bubba. And so the St. Bernards are left behind, and they have a positive charge. So the Chihuahuas have all left. Okay, so visualize this. The Chihuahuas have left. The positively charged St. Bernards are left behind inside my hand because the Chihuahuas have migrated. So what happens is that when I put my hand there, it's an electrostatic attraction. My hand itself is actually neutral. It isn't like I'm negatively charged, okay? Which would be really weird if I was. I'm neutral, okay? But what happens is that within my hand, I create a region that's positively charged because the Chihuahuas have left. The St. Bernards are left behind. So when I do that, the positively charged St. Bernards are attracted to the Chihuahuas in the balloon, and it makes it look like I'm doing magic, okay? So what happened before I had this thing charged, when it was just a balloon like this, okay, like that, nothing happened because there was an equal number of Chihuahuas and St. Bernards. When I rubbed the balloon, I put an excess number of Chihuahuas on the balloon. It became negatively charged. Now, that's why it becomes attracted to my hand. Okay, so now we're going to step up again. Oh, back you go. So, you can go back for a second. Got it?
Yeah.
Okay. So now, I've loaded up everything with Chihuahuas.
2 giant electrons.
So now,
Oh my God.
okay, so now the Chihuahuas don't like each other. Now I'm actually going to push that up there. Okay,
That's sick.
And now
so now, yes, the balloon is stuck up there. So what happened up there? Why is that balloon able to defy gravity, Gannon?
it's because the ceiling's got a positive charge.
Why?
Because the electrons in the balloon are
Chihuahuas.
Chihuahuas are
Okay.
pushing away the other Chihuahuas,
Yes.
leaving behind only St. Bernards, who attract the Chihuahuas to it.
Beautiful. Okay, you've explained what happened with dogs. Okay? Now, on the ACT, okay, it's like, where are the dogs? We have a story about particles. Where are the dogs? Okay, who let the dogs out? Okay, so this isn't magic, right? It isn't like, oh, there's a gravitational source up there in the sea. No, okay, I can do it with this one too. Okay, oh, maybe I lost my charge. Oh, kind of. Okay, tried to stay. So, but what's happening is that force is stronger than the gravitational force trying to pull it down. So, you wouldn't think, oh, the electromagnetic force isn't that strong. It's actually exponentially times stronger over the same distance than the gravitational force is. Okay? So, you wouldn't think these electrons, protons, neutrons, oh, what's the big deal? On a relative amount of force, it's really, really strong compared to gravity. If gravitational force was the same strength as the electrostatic force, the universe would have never formed. You would have had the Big Bang, and then you would have had whoop, the Big Crunch.
Yeah.
Okay, would have, okay, that would have been, it's like, oh, well, that was fun. Brilliant. Okay, good. God's going, well, that was a waste of a universe. Make that electrostatic force, or make the gravitational force too strong. So, that's the balance that you have to strike. Okay, so got that idea. We're good? Okay, now, bring that camera. Let's go to the back of the room.
Take care of the balloon.
Yeah, we'll just leave it. Well, actually,
I just wanted to hold the balloon.
okay, is that all?
Yeah, that's really all. That was it.
And it's also what we call a convex mirror. We'll study optics later on. So when I look at it, you can kind of like see yourself, but it's distorted because the light's hitting off and it's bouncing off at different angles. And this actually acts as like a mirror. So, and later on, you see why we call this a convex mirror. If it was like curved inwards like this, it would be a concave mirror. So this is just one big convex mirror. So what happens is that when I'm going to turn this on, this is going to begin to generate a whole bunch of electrons up here. So it's got this rubber band that's going to spin, and it's going to carry the electrons from down here up to here and drop them off. So this thing is going to become very negatively charged very, very quickly, okay? So, to show that, I'll put this up here, turn it on. Okay? So, if I move my hand around it, I can kind of do this Jedi mind trick thing. Okay. Me and Yoda were tight. Okay. So, here's the deal. So, what's happening? Ooh, hold on. Hold on, I'm going to get shot. Okay. As many times as I've done that in my life. So, okay. So, what's happening for that to do that? Again?
As electrons are moved.
No.
As chihuahuas
There you go.
are moved up into the ball, they put out a negative force.
Yep.
So it pushes anything that has a positive force away from it. So it's pushing those away, giving them it's pushing all the chihuahuas from it away,
Yes.
giving it a positive charge.
No. Yeah, that's going to be positive, but that up there is going to have
Negative.
negative. So what's happening is that chihuahuas don't like each other. Okay, nor should they, if you've ever been around chihuahuas. Okay? They're just vile little creatures. If any of you have a pet chihuahua that you're madly in love with, is anybody in that situation? Really?
There's a Chihuahua Pomeranian.
That makes it a little better.
So it's like a chihuahua, or I don't know what they call it. Is it cute?
That depends on who you ask.
Yeah, it's pretty cute. It's pretty cute.
Okay. Does it yip a lot?
No.
Okay, well then I can
Okay,
tell.
non-passive. It can-
Okay. So, what's happening is that when I turn this on, since the chihuahuas don't like each other, so those chihuahuas are all flowing out, and they don't like each other. So they're trying to get as far away from each other as they possibly can. So when I put my hand here, okay, so my hand then, okay, we're creating an oppositely charged situation. So when I put my hand here, this thing is becoming attracted to my hand because you have a distribution of that charge. So when this is going on, they're all as far away from each other as they possibly can get. My hand then creates that disturbance where they become attracted to that. Okay? Got that out. All right. Okay.
Don't you have a grounding rod right
I do, but
there?
that's not nearly as much fun. Okay. I'd rather risk a heart attack. All right.
There's always that.
There's always that, you know. Physics teacher, you know. Okay, so now I'm going to put little bits of paper up here.
I thought those were really eyes.
What?
Googly eyes from here.
Oh, okay. All right, I can see that.
That's
Okay.
not they were.
So I'm going to turn this on, right? Ooh. I think I just inhaled one. So, what happened right there? Now again, you've answered enough. Joelle, what happened? Okay, let's articulate this. You're right, this happened. But why did this happen?
So is the ball like negatively charged?
Yes?
Okay. So the chihuahuas want to go away from the other chihuahuas.
Exactly.
So the paper had to be negatively charged and then it repelled it.
Beautifully. Okay? So, now if you look at what happened, okay, and I'm going to kind of put some, if I can get one to just stay. I'm just trying to get one to,
No way it's this.
well,
That's something.
if I get rid of enough charge,
You want somebody to come over there and zap themselves for your
because
sake?
I got to have a little bit
I
of
will
charge.
not be.
Okay, there we go. Oh, got it. Okay, so very briefly, I can make it dance. So, very briefly, it was like standing up. So what happened when it was standing up, that little bit of paper, okay, the googly eye, right? Because this whole thing is negatively charged, it was making those electrons go far away from the source as it could. So the chihuahuas are moving up there. It left the St. Bernards down here. So that's why that was able to stand up. So, just kind of see it standing up a little bit, okay? But it's the same idea. Those electrons, or those chihuahuas, are being pushed away. The St. Bernards were left behind. You had a positive and negative region. It all goes flying off. Okay, now. Okay. So, I need the balloon. I'll give it back. I promise. Okay, I just need it for a little bit.
Okay.
Okay. Now, if I take this balloon and I put it over the bits of paper, right? Nothing happens. The bits of paper are being pulled down by the earth, okay? The balloon has a certain amount of mass and it's being pulled up by the balloon. Obviously, the gravitational pull going down is stronger than the force from the balloon acting upward. But if I take that balloon, okay, and I charge it, and then put it over there, then I can pick up the paper. But again, look at what happens on the paper. The paper, because the balloon is negatively charged.
Kind of like peeling off of it. Kind of like
Standing up.
Well, you're not peeling it, but you're just making the chihuahuas move.
that. Yeah.
So when I do this, okay, I'm making, like this one, standing up right, well, it was standing up right there. So the chihuahuas went to one end, the St. Bernards were left on the other, the positive end was attracted to the balloon, and I was able to pick that up. So if you're really, you know, lazy, and mom wants you to like pick up bits of paper in your room, and you happen to have a balloon, okay, you can just do that, and then you can pick up bits of paper. Now, speaking of this, Ken, so with this balloon here, charge up this. Now, if I put this balloon directly over the top of the can, nothing happens. But if I put it off to the side, stop, come back, whoa. So I can make the can roll. So how can I make the can roll using a balloon?
The chihuahuas don't like each other.
What?
The chihuahuas don't like each other.
So what?
So those chihuahuas are pushing those chihuahuas away.
And what's happening? But what's left behind?
The St. Bernards.
The St. Bernards are left behind.
And they also don't like each other.
No, the St. Bernards love the Chihuahuas because they're oppositely charged.
Oh, right.
Okay, the St. Bernards like the Chihuahuas.
Oh, no, I meant the St. Bernards don't like the other St. Bernards.
Oh, that is true. That is true.
Yeah, I was like,
But we'll get to what's happening with the St. Bernards later.
Okay.
Yeah, you're right. The St. Bernards don't like each other either.
Yeah.
They hate each other. But that has to do with something else. Okay?
Okay. Sweet.
So, when I do this, what's happening is that there's a region on the can where the Chihuahuas have run away. The St. Bernards are left behind, and what happens is that region is continuously changing. So if I just gave this to Josh and I said, hey Josh, make it roll. Oh, okay. He'd apply a torque to it to make it spin. So what's happening is by doing this, we're creating a torque by that oppositely charged region, which is creating a force which is making this thing spin. Now, one of the things about electric fields is that just looking at it, you can't tell if there's an electric field. I can't look at that sphere and go, oh, is it positively charged? Is it negatively charged? Is it charged at all? Now, this is true of electricity. Unfortunately, okay, you can touch it and go, okay, all right, it's neutral, right? Okay? But if it was charged, and I do that, okay? And I can't tell it, but now if I put my hand out, okay? Then that's how I know that it was charged, so I can't look at it. So one of the things that we've got, and this is actually, you're the first class to actually get some experiences. So last year I bought this new toy, okay? It's called an electric field sensor. It's cool. So what I'm gonna do is that, like if I put my hand here, okay, I'm pretty much neutral. But if, give me that blanket if you would. Okay, again, can you hold that balloon? Okay. So now if I take this and, what happened? Hold on. Well, yes. Hold on. Huh. Okay, well, this was really cool. Ah, there we go. Okay, now it works. Okay, so, so what's happening now, and this is actually shows this inverse square relationship. So if it's negatively charged, it goes into the negative region, it goes blue. So, but what happens, you'll notice that as Gannon takes that balloon away, then we become positively charged, but then as he brings it closer, that balloon is negatively charged, and then we max out the scale. So this is a function of distance. So that electric field strength around that balloon is an inverse square relationship. So the closer you are to the balloon, the stronger the electric field is. The further away you are from it, the weaker it is. So now, if I move this towards the blanket, you'll notice that the blanket is showing a positive charge. So what happened is that the balloon stole the chihuahuas from the blanket, okay? And now the chihuahuas are over there, and the chihuahuas, there we go. Okay, we got to recharge it. Hold on. Hold that. No, hold that.
Oh.
Yeah, it was the wrong battery you grabbed. So now, when I bring that closer, now I get this huge negative charge. So this has excess chihuahuas, this has excess St. Bernards. So the chihuahuas left the blanket and moved over here to the balloon. So we can't see it. But what this allows us to do is get a visual for what's actually happening and what's taking place. Got it? Good? Rand? Okay, back we go.
Going rolling
Yes.
back.
Yes.
I do.
Are you happy now?
Yeah, I decided that their names are Cosmo and Wanda. I think that's fair.
I mean, yeah, you got a pink one and a
They're
green
really
one.
all parents.
Yeah.
Oh, Terry's good.
So this one's what?
That's Cosmos and Wanda.
Okay.
I can write their names on them if you want.
Please do.
Do you have a Sharpie?
Hold on, just go grab like,
Dark turquoise.
Tanner always said that he hated electromagnetic fields because he couldn't see them.
I know, now he can. He's gonna be upset though.
He will, he will. He tends to watch our lectures in his free time.
The meeting is ending.
What?
I think it's
Because he
fine.
has nothing
No one's
better
in
to
it.
Yeah,
Fair enough.
I'm just gonna keep it off.
okay.
That's why I need to get a Zoom call invite and send it to him.
Okay. All right. So, when you talk about the electromagnetic force of all the forces is the most diverse, okay, but it's the most important. So electromagnetic force is going to affect anything that has charged particles. So for example, if you look at our universe, and our universe is actually really, really cool. I mean, the more you study it, the more you sit back and you think, this is just cool, okay? Because if you look at every electron that we've ever studied, this is the ultimate production system. Every electron that we have ever studied has the exact same mass, has the exact same amount of charge, okay? And, and later on you'll see, you'll just learn this number. But every electron, oh, are you going to be stupid? 0 times 10 to the negative 19 coulombs, okay? Every electron has that amount of negative charge. And it's this tiny, 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 tiny bit of matter. And then you have every proton in the world, or in the universe, that we've ever studied has that opposite amount of charge. But it takes about 1,800 electrons. If you were to make a balance, it would take about 1,800 chihuahuas to balance out one St. Bernard. Okay? So you would think that these electrons that are so much smaller and are moving around so much more quickly would have less charge than the protons do. But they don't. They have the exact same amount of charge, which is why overall everything is neutral. So it isn't a function of mass. And then you can get into a philosophical things like, why does it have charge? What creates the charge? You know, why was the universe made that had both positive and negative charge? And then, glad it happened that way, we wouldn't be here having this discussion. And then why did we make these random neutrons? Okay, seriously, what role do neutrons have? We're glad they're here, because if you didn't have neutrons, you couldn't build a stable nucleus, because the neutrons balance things out. So it's like, neutrons, okay, they're cool, but why did the universe make those? Why did the universe have a certain amount of gravitational force? If the gravitational force had been stronger, we wouldn't be here having this discussion. If the gravitational force was weaker, we wouldn't be here having this discussion either, because stars would have never formed. You would have never formed hydrogen into helium, and the universe would just be like this cold, dark mass of particles moving around. Okay? And there would be no light. And so later on, when we get into entropy, and you see that the ultimate fate of the universe is that it's actually, at some point, the universe is just going to die out. Because eventually we're going to run out of hydrogen, the stars are going to run out of fuel. I know, it's kind of depressing. But that actually impacted, once they figured this out, it impacted like the great thinkers of Europe, and they actually went through kind of a depressive state, because they're going, no, it did. I mean, because they're going, wow, the ultimate, everybody thinks, oh, the universe is immortal, and, human beings, and it's like, no, we're kind of screwed in the long run. Okay, now again, is it anything to worry about? No, but in the long term. Oh, yeah.
We should have a funeral for it. Just so, because we know what's happening.
Oh, no, we're going to screw it up well before that.
I agree,
Okay.
100%.
I know.
Some other species can come along and do that.
Huh?
I said some other species can go.
Well, that
Simulation.
Okay.
So.
So- if you look at this electromagnetic force, there's a whole bunch of cool things that we can do with it. So even if you look at like the solar array out there, okay, that solar array works because of the electromagnetic force. So if the process is that the sun is generating hydrogen and turning it into helium, out of that process you're turning mass into energy. The sun emits these bundles of light or energy that we call photons. They travel from our nearest star, they strike the surface, takes about 8 minutes for it to get there. They strike the surface of the solar array, it hits this little chihuahua, and the chihuahua has enough energy, it goes, yippee, okay? And it jumps out of its normal realm around St. Bernard's. We collect all those chihuahuas, we turn it into electricity, and I can make toast. Okay, because that's how any electrical story ends, is that the ability to make toast. Because that's why we have electricity, because we want to make
Toast is
toast.
so good.
Okay, it is. And so that's how it works. So if you look at what's holding you together, your DNA, your cells, everything, every bit of matter that holds you together exists because of the electromagnetic force. Okay, without that, we wouldn't be here having this talk. And it's even cool if you think about, on an atomic level, what happens for you to write with a pencil. So one of the cool things we've done as a species is develop the ability to manipulate the electromagnetic force. So if you think about what happens for you to write on a piece of paper. So the bits of matter, the graphite that hold the lead together, are strong enough to hold it together to make up the pencil. But then when you write, okay, so here's that piece of graphite, here's the piece of paper. So what happens is that it forms a bond between that graphite and that paper that's strong enough to basically tear it apart. So when you write on an atomic level, you're tearing apart those bonds that hold that together as graphite. Now, graphite is basically nothing but pure carbon, okay? If you arrange those pure carbon atoms in a different way, you get a diamond. So, but if you try and write with a diamond, guess what?
You can break the big time too.
Yeah, all you're gonna do is just tear the paper, okay? You're not gonna be able to write with a diamond. It's like, oh, honey, I forgot my pencil. Can I borrow your diamond ring? I need to make a note, okay? No,
That'd be
okay?
cool, though.
It's not gonna happen. But diamonds, by the way, ladies, if you're given a diamond and say, oh, diamonds are forever, they're not. Diamonds eventually change into graphite, okay? It takes billions of years, but diamonds aren't forever. All carbon will eventually end up as graphite, okay? It's a very, very slow process. Don't worry about it. Again, we're gonna have a whole bunch of other things to worry about, okay? So, but gentlemen, don't get cheap and buy, give her a chunk of
Moissanite.
Kingsford charcoal and go, if this was a diamond, honestly. Science happened and now it's, now it's carbon.
It was.
okay? It was. Honest to God, when I bought it, I paid $10,000 and it was a diamond, okay? Ask Burkamp, he'll vouch for me, okay? I will roll you under the bus. I'm going to tell you this right now. Fellas, I will roll you under the bus and go, oh dear Lord, honey, he's an idiot. Run away and hide. Okay.
Breaking
I'm just-
apart marriages.
Huh?
Or I guess they weren't married yet. Breaking apart relationships.
Relationships.
Yeah.
Yeah, okay. So, but that's kind of cool. Now, let's say you, God forbid, as teenagers, you make a mistake. What do? You erase it. Oh, you take an eraser, right? So what happens there?
It's
You
the
break
exact
the bonds that hold the graphite onto the,
paper.
and it lifts it off. Oh, that's kind of cool. Laundry detergent. How does laundry detergent work on an atomic level?
It's like non-polar and polar bonds.
It breaks the bonds that hold the stains onto the clothes, right? But it doesn't break the bonds that hold the clothes together.
That is so cool.
Oh, no, so it is. Okay, now, look, you have bonds that hold your hands together, okay? Right? It's kind of cool. If you didn't, your hand wouldn't be here. But even though your hand and your hand over here, both are all the same you, okay? But when you clap the hands together, they don't like each other. It isn't like you have to worry about clapping your hands and all of a sudden like part of the skin from this hand sticks with this hand over there, okay? It doesn't. Even within the same hand, it's just like, whoa, Lauren, okay? The sound of one hand clapping, okay? Like this. I can't do it with this hand, I can only do it with this hand. You stop, it's like, God, it's flipping you out.
It just feels so weird. Like it's illegal or something.
Like it's illegal? In Arkansas, it is. I've been arrested in Arkansas for doing that.
Just like
I was in
really.
Little Rock, Arkansas, in a bar on a Saturday night, and a true story, and I did that, and I was arrested. Okay.
Just like how
I
you're
was just
arrested in
threatened with it. I
Africa.
wasn't actually.
It just looks like it's not supposed to happen.
Well, at some point, we'll get out like the strobe, and we'll look at it in slow motion, and then it gets really weird because you hear it clapping really quickly, but you see it just going like this in slow motion. I won't do that. I won't do that on a day you're gone, because it will completely push you over the edge.
I don't know why it trips me out so much.
I know, it's just like, dude, I have done that demo God knows how many times, and I have never, ever had anyone just completely go, wah!
Sorry.
It's okay. Okay, I guarantee you, this is a day you would never forget. You got a hold of the lemon and you got flipped out by my hand.
Yeah, and my 8th grade science teacher used to do that too, and I had the same reaction.
Did what?
Or
This?
not science.
What
No,
happened?
my music teacher used to do that, and it tripped me out.
The one hand clapping?
Yes.
Which I'm never going to do again, I swear to you. I'm never
Okay.
going to
Biggest
do
lie
again.
I've heard.
Okay.
I know you're gonna forget and do it, and then I'm.
No, I won't. No, I won't. I promise you.
Okay.
Okay, because this was like the only time throughout the year that I do that, okay? Now, is it okay if I do this?
I thought you were gonna do that. And I was
No, I can't, no, I didn't.
no, that's fine.
This is good.
Yeah, that's normal.
And this, I'm not doing it. It's bad. Okay, duly noted.
I just,
With YouTube as my witness,
I'm not supposed
Okay.
to do that.
I'm not going to do that again.
Okay.
Okay, all right. So, at this point in our story, physicists had come up with two fundamental forces. gravity and the electromagnetic force. And they thought they were cool, right? They could do electricity, we could make light, we could feel heat, we had everything sorted out. And so this is like in the late 1800s. John Dalton, if you remember from Chem 1, had come up with his working atomic theory. Said atoms combined in whole number ratios, all atoms of the same element are identical. You know, it was the first real working idea, okay? And Dalton actually stole the word atom from the Greek word atomist, because they were the ones that first came up with the idea of the atom. So if you translate the Greek word atom, it means indivisible. So John Dalton actually went back to ancient Greece, and that's how he came up with the word atom. So this is going to be important. In Dalton's atomic theory, atoms were indivisible. Not invisible, okay? Indivisible. So he saw the atom as the most fundamental building block of the universe. So in his mind, and this is how this would play out. So imagine that you have a chunk of pure gold, okay? And you have this infinitely sharp knife. And you take this chunk of gold and you whack, and you cut it in half, okay? So you take this piece of gold and you cut it in half. It's still gold. Now, if you think about it, that knife can only go in between the gaps of these particles. It's just like if you're a football running back and you're trying to run ahead, you don't want to run where people are standing. You're going to go through the gap in between. So the same thing is true of this knife. This knife is going to go in the gaps in between these particles. So imagine that we cut it in half, and then we're going to take that piece and we're going to cut it in half. We're going to keep cutting it in half and cutting it in half and cutting it in half. At some point, we will reach this fundamental particle that we cannot divide anymore. There's no gap, okay? And that's in the atomist world of Greeks, and what Dalton revisited. That's how they viewed the atom. So if you look, so this is a lab manual for physics from 1920.
Yeah.
And this wasn't mine, okay? But if you look at the back on the appendix, there's no mention of electrons, protons, neutrons, okay? There are no subatomic particles listed because they hadn't found them yet. So even 100 years ago, there was no mention of subatomic particles. Now, along comes J.J. Thomson. Anybody remember what J.J. Thomson did out of your Chem 1 studies? He discovered the electron by using a cathode ray tube. So a cathode ray tube is a piece of glass that looks like this, okay? And there's a positive and a negative end on it, and basically you run an electric current through it. And it creates this stream of particles.
Oh, yeah.
And what J.J. Thomson was able to figure out was that they were negatively charged. And so at this point, they found the first subatomic particle, which was the electron. So if there were electrons, which were negatively charged, they also had to figure that there were positively charged particles because the world overall was neutral, okay? So at this point, and this is what always makes the physics department laugh, because the chemistry department tells this story in the structure of the atom. And there were certain big hitters like J.J. Thomson, Ernest Rutherford, Niels Bohr, Erwin Schrödinger. They were all physicists, okay? The chemistry people were trying to figure out how to purify cocaine and make money.
They're doing it.
And they still doing it, okay? Nothing's changed. So the physicists were going, but literally, because here's the deal, in the physics department, everybody was kind of depressed because they had gravity figured out, they had the electromagnetic force figured out, okay? And literally, the scientific community at that time was kind of depressed because literally their thought was, we've got the universe figured out. We're going to have to tweak some constants, things like that. Literally, they thought everything had been discovered up to that point. So then Thomson comes along and goes, wow, there's electrons. It's like, oh, okay, well now there has to be protons to balance that out. So Ernest Rutherford comes along. Now you got to understand Ernest Rutherford. Ernest Rutherford was a physicist. Okay, and at the end of the day, physicists like to smash things, okay? So here's the classic story, and I'll leave you with this story. So this is how a physicist would approach a problem. So let's say that you give a Volkswagen Bug to a physicist, and you go, hey, what's the Volkswagen Bug made of? I don't know. Let me give the Volkswagen Bug up to about 10 miles an hour and I'll smash it into a wall. Okay, it smashes into the wall 10 miles an hour. It's like, oh, look, a little bit of the bumper fell off. Okay, there's some bumper. All right. Well, if 10 miles an hour is good, 100 miles an hour has to be better. So then he gets it up to 100 miles an hour. He runs that into the wall. Like, oh, there's glass. We have glass. We've got glass flying off of it. Okay. Well, let's get it up to like 500 miles an hour. Smash it. It's like, oh, there's an engine. Cool. How cool is that? Okay, there's an engine. What's the engine made of? I don't know. Let's get two engines going together at about 1,000 miles per hour, and we'll smash the engines together. Oh, look, a piston came flying off. There's a piston inside the engine. What's the piston made of? I don't know. Let's get the piston going like the speed of light, and we'll smash the pistons together, and we'll see what goes flying off. And that's fundamentally the story of how particle accelerators work. So particle accelerators work by taking subatomic particles and getting them up to speed and smashing them together. Okay, so here's what's going to happen. I'm going to go ahead and give you the lab that your other group is going to start on tomorrow. And unfortunately, this is just going to be horrible timing with the lab. On Wednesday, I'm going to have a video for watch that's going to explain more about the lab. Okay? And then on Thursday, you guys are going to get like the second half of the data. That's kind of see how I see this deal playing out. Because this lab takes like 2 days. So I think what's going to happen tomorrow, the other group is going to get like the first half of the data that they will share with you. And then on Thursday, you guys are going to get the second half of the data that you're going to share with them. And then on Wednesday, I'm just going to do a video that explains more about the lab. Okay? So that's kind of how I hope to deal with this. All right. So, no, that's not it.
I need to get rid of my sister.